Slow 4. 1, 2, 3, 4.
Bless the Father, bless the Son, cross your heart, 'cause you're the one collecting moonbeams in the morning. Curvy sticks and wooden poles assisting you in plugging holes. Plug them holes till you see straight through to the mind's eye. Think about it, turn around and go back to the quiet sound of Jim and Dan prancing around the pool. You were the fool, and I feel sorry for you. You were the fool, but there's something you can do. You can wash your arm in a pool of mud. You can chop a tree, prevent a flood. You can speak with a turtle just by flipping him around. You can build a boat, sail the sea. You can buy a mold, forge a key, initiate the sequence, create catastrophe. Think about it, turn around and go back to the quiet sound of Jim and Dan prancing around the pool. You were the fool, and I feel sorry for you. You were the fool, but there's something you can do. Bless the Father, bless the Son, cross your heart, 'cause you're the one collecting moonbeams in the morning. Curvy sticks and wooden poles assisting you in plugging holes. Plug them holes till you see straight through to the mind's eye. Think about it, turn around and go back to the quiet sound of Jim and Dan prancing round the pool. You were the fool, and I feel sorry for you. You were the fool, but there's something you can do. You were the fool.
So on Friday, we went through all three of these techniques for proving big O analysis. If given a function f of n, you need to show that it's big O of g of n. And the first one is easy, but only if finding roots is easy. So we're not going to do that one, especially for when we've got like logarithms and exponentials. You're not finding roots very easily with those. Technique B is the one that we're probably going to prefer because technique C requires some calculus. If you're comfortable with calculus, go ahead and use it, right? But otherwise, we're going to simply use algebra over here. Before we do that, let's talk about the categories of functions that you'll probably are most likely to encounter when you're doing algorithm analysis, right? So one of those categories of functions are constants, right? So for example, you're doing a formula computation. Formula computation where, you know, it's just b squared minus 4ac, then taking the square root of that. You're doing a certain number of additions, a certain number of multiplications, a 1 square root. In other words, you're doing a constant number of computations, right? You can also consider, oops, so come on over here, right? What's slightly larger than that? Give me the next one. We're going to work smallest to greatest. Give me another function type that you've seen before. Linear, right? So order, n, right? And this came up when we did linear search, right? Anytime that you've got a collection that you're iterating over, so collection, iteration, right? et cetera, et cetera. You're probably looking at a linear amount of work there. What about sandwiched in between those two things? Yeah, logarithmic, right? So order log n. And remember that all of our bases are with respect to base 2. Let's do it like this. There we go. Log n, right? And this came up with binary search, or binary insert. Anytime you're doing something that is breaking it down into half each time. The input is cut in half, cut in half, cut in half, cut in half. You're going to have some sort of logarithmic behavior there, right? All right, so what about larger than linear? Quadratic, all right, quadratic. And that's when we've got a quadratic value, right? N squared, right? And that came up when we did selection sort, insertion sort, right? And it also came up when we did a bad linked list iteration, right? That was what started all this entire module out, right? Where we were doing it using n squared, and it would have taken us 20 years to do that on moderately large data, only 1 billion elements there, right? So as we can see, like anything above quadratic and above is probably not going to be practical on most computers, or even going into the future here. Fortunately, we have something sandwiched between those two, right? Where it's the sweet spot of algorithms. If you can find a quasi-linear algorithm and order n log n, right? Algorithm, right? We call it quasi-linear, almost linear, right? It's almost linear except for this logarithmic factor over here. That logarithmic factor is almost nothing, though. Remember, what's the growth rate of a logarithm? It's like 1 over n, right? The growth rate is actually decreasing. So for all intents and purposes, you could probably ignore that logarithmic term in there and make it linear, except that the logarithmic term is still there, so it's quasi-linear, right? And this is good sorting algorithms, good sorting algos, like say merge sort, or quick sort, or tim sort, right? Or yeah, that's all we're going to look at, right? Tim sort, basically, we're going to look at the end at heap sort. That's what I was thinking of, right? But we need to understand what a heap is first, which is going to be the next module, right? Towards the end of the next module, okay? All right, what's above quadratic? If you just keep going as far as polynomials are going. Yep, cubic, right? And cubic, we haven't seen anything like that, but it's common to see, say, matrix multiplication or other operation on a matrix. Because there, you've got n squared things in there. And so if you go over each row and each column, you're n squared already. If you're doing some work within that, then you're doing a linear amount of work within that, then you're doing n cubed. You've got three for loops, for each. Then you're going to have n cubed there. Right? Of course, you can generalize that to any polynomial. But like we said, once you're at quadratic and above, you're pretty much toast. You're going to be waiting for, say, 20 years on moderately sized inputs here. Okay? But now you're getting in the realm of completely unacceptable, say, exponential, order n squared. And note here that not all exponentials are equal, right? In other words, 2 to the n is going to be order 3 to the n, right? That's true, but 3 to the n is not going to be order 2 to the n there. Once it's all rendered, you'll see it, right? In fact, if you take any base, alpha, and then another base, beta, that is slightly bigger, then it's going to be the big O is going to hold, but the reverse will not, right? They are not created equal, right? So if you've got a base 2, great, but if you've got base 3, then it's even bigger and bigger and bigger, right? Where might you see something that is 2 to the n? You've done 235 sets so far, right? The power set, right? Power sets, or considering all possible subsets. Those are also called, aka, also known as combinations, right? In other words, all n choose k. Let's write it like, is it rendering? Let's find out. There we go, n choose k for all k, right? How many sets are there of size 0? N choose 0. There's 1. There's the empty set. How many sets are there of size 1? The singleton sets. N choose 1. How many? 2. N choose 2. Those are pairs. N choose 3. Those are triples, right? Dot, dot, dot. How many ways are there of choosing everything? N choose n. That's 1, right? Those are the binomial coefficients. Also defining the binomial distribution. Also summing up to 2 to the n. Right, when you sum them all up, the power set, okay? So if you're ever doing anything with combinations or combinatorics, right? Super exponential, right? Say order, what is this guy right here? Factorial, right? Factorial. Right. So factorial, right? Even bigger than any exponential. Right. Where would this come up from 235 in combinatorics? Permutations, right? With or without repetition, right? With repetition, now you're super exponential. But permutations, right? Arrangements of distinct elements, okay? And that's going to be if you got 10 people and you want to arrange them, to take a photo. The number of ways of doing that are 10 factorial, because the first one, you can choose any of those 10 people to put as the first one. You can choose, now there are only 9, so you have 9 choices for the second one, 8 choices, 7 choices, etc. Right? Super exponential would come up if you are computing all the possible card shuffles, 52 factorial, right? At this point, you're talking about not being able to compute anything within the lifetime of the universe, right? Much less your lifetime, right? Of 20, you're going to live longer than 20 years, hopefully. But, we're on the scales of dozens of years now, right? Hopefully I'm going to live longer. Hopefully I'll live to see that computation right there, right? But otherwise, you're talking about, not within your lifetime here for large inputs. Here you're talking about not within the universe's lifetime. Right? So keep that in mind, that once you've figured out, nope, this is going to be exponential or super exponential or whatever, then the jig is up. You can't do it. Right? Let's do some examples before we move on to a recursive algorithms. So examples. Right? And these are the examples I did in the last one. So maybe I'll switch it up a little bit with, come on, move it over there. We can select, these are always hard coming up with because, of course, they're all unnatural. And when you randomly generate a bunch of functions, it's like, okay, is there anything that's actually interesting with them? This first one is super easy, but it demonstrates how easy that technique approach B is, right? So we want to show that f of n is big O of g of n, right? So we're going to set up our inequality here. 2.5n less than or equal to. You need to make this look like less than or equal to c sub n, which is equal to c sub g of n, because that's what g of n is. It's just n. Right? Well, at this point, you're already done, right? This is less than or equal to 2.5 g of n, right? And so for n naught being 0 and c being 2.5, the inequality holds and you're done. Right? It's that simple. But if you have functions that don't involve, straight up polynomials like that, what happens? For example, n log, and then we've got 64n inside there. We want to show that this is big O of n log n. We have that intuition because all you need to do is say, well, that's a constant, and constants don't matter. So what if we got rid of that? It looks exactly the same, right? So we can't just get rid of it in algebra, though, but we can work on it. 64n, there we go. All right, what is that equal to? And again, don't lose the forest for the trees here. You need to make this look like c n log n, okay? What do I do there? Yeah, this is log of AB, which is equal to log A plus log B. So don't lose that n out front. Oops. Log of 64 plus log of n. Our bases are implicitly 2. So what's log base 2 of 64, which is why I chose 64, so it'd be easy. It'd be what? Careful. Yeah, 2 to the 8th would be 256. Right? That's 8. That's that's a byte right there. That's your ASCII text table, right? 0 to 256, 255, 256 possibilities. It's 6 plus log n. Right? Algebra, 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 and you have n log n plus, and then what happens here? 6n. All right, how do I make it look like that? Is this true? Is 6n less than or equal to 6n log n? Log n is a monotone increasing function. Generally, yes. Is that true for, so let's go ahead and make it that big. But is it true for all n greater than or equal to 0? For all n greater than or equal to 0. Right. Well, what happens when we plug in 0 over here? We get 0 on the left-hand side. 0, but what happens to our log 0 here? Is that well defined? Nope. Even if you wanted to and say, oh, we'll just say that it's negative infinity. Is 0 less than or equal to negative infinity? No. And by the way, what's 0 times negative infinity? Is it? I don't know. Is it? I thought it would be undefined.
What? Anything from 0 to
0
0?
times negative infinity. Let's ask what. Vote. Okay, we'll put it up for a vote.
Open up on the Substack.
Negative infinity times 0. Undefined. All right. Yeah. Thank you, Wolfram Alpha. All right. So, nope. The votes have been counted, and Wolfram Alpha is the only vote. Right. So, is that true? No, it's undefined. Is it true if I went up to 1 though? 1, 1. So this is going to end up being 6, less than or equal to 6 times log of 1 is what? 0. It's not even true for 1. Right? Okay. So what if we went up just 1 more? 6 times 2, that's going to be 12 over here. 6 times 2, that's 12. Now log of 2 is 1. Is 12 less than or equal to 12? Yeah, and after that, it's always going to be true. So you do have to be careful here, right? Especially when you're working with logs and exponential functions or whatever, right? This is only true for all n greater than or equal to 2. So this is equal to 7n log n. And for c being 7, and careful, n naught is now equal to 2. Not 0, not 1. It's okay to push it over a little bit if you need to make all these definitions work. Remember that there are an infinite number of pairs. You just need to find one pair, that is. Right? Because we had 6n log n, n log n, that's 7n log n. Right? It was just this one, right? Yeah, exactly. Addition right there. Yep. Okay. All right. Two couple more here. What if I said that f of n is n 2 to the n, and g of n is, say, 3 to the n. Right? By the way, since this is the honors section, let's just go ahead and try this with, in fact, let me simplify this initially here. Right? Let me try this with limits first. Limit as n tends towards infinity of 2 to the n, 3 to the n. I've got a monotone increasing function at the top, a monotone increasing function at the bottom. What is your initial, reaction to doing something? What tool are you going to use? All right, L'Hopital's law. Do you know what the derivative of the first derivative of 2 to the n is? It's natural log of 2 to the n. Right? Why? Because what is the first derivative of e to the x? E to the x. What does that tell you about growth rates of exponential functions? They're still exponential. What does that tell you about the growth rate of exponential functions? Still exponential. You will never get rid of them, right? And likewise over here, this is going to be a natural log of 3 to the n. Did I make any progress with L'Hopital's law? Nope. This is just a constant that would sit out front here. Okay. What should I have done first instead of bringing a sledgehammer to a finishing nail? Look for algebraic simplifications first. We have a common exponent, right? What's going to happen when you take something that is less than 1 and then you take a power to it where that power is increasing? It's going to get to 0. Right? In other words, this is big O of that. Right? All right. I just wanted to do that to show you that no, L'Hopital's law is not the be-all, end-all. Right? Algebra first. Okay. Let's go ahead and set up our inequality here. Right? I want to show that this is less than or equal to ... c 3 to the n. All right, well, I need to make one of those bigger. Clearly, I'm going to make the smaller one bigger so I can fold it down into just one expression here. Basically, I've got a function of n and a function of 2 to the n. I want to fold that into one function. What if I tried this first? 2 to the n times 2 to the n. First of all, is that true? Right. Is it true for 0? 0 and 0? Yep, because that becomes 1. Is it true for 1? Yep. Is it true for 2? Yep. Is it true for 3? Yep. ... Oh, so it's true. What does that equal to? Two to the 2n, and what happens? What can I do with that 2 to the 2n? What can I do with that 2? Bring it down, and it becomes what? 4 to the n. I've overshot my goal. Right? I wanted to make this look like 3 to the n, but instead I made it even bigger than that. Right? It's got to be bigger, but not too big. Right? If you make it too big, then you're not showing this inequality here. All right, back it up. Can't go that far. I could make it into n squared, 2 to the n. But does that really help me in collapsing those two terms? Nope. Here's another one. I don't think anybody would have thought of this, but oh, well, if I get them both into 2's, then what I can do? 2 to the n plus 1. But is that even true? Is n less than or equal to 2 for all n greater than or equal to 0? 0 and 1 and 2, that's true, but what about 3? Is that true? No. So that's not even true, right? Okay. It's computer science too, for the random internet folks that come in. Right? All right. So what can I do? I just went too big with 2 to the n. What if I did something smaller? 1.5 to the n times 2 to the n. First of all, is that true? 0 and then 0, that works. 1 and 1, that works. 2, and then what happens to 1.5 squared? 2.25, I think. 3, and then 3 over again, it's still going to work. Why does that help me get to this one right here? What is 1.5 to the n times 2 to the n? Common exponent, do what? 3 to the n. So for c being 1 and n naught being 0, the inequality holds. Okay? Just have to make it bigger, but there's an art to making it bigger. You can't make it too big. You can't make it big with and it not be true or whatever. Last one. What if I had n factorial here? Can I show that this is n log n, that quasi-linear thing? Now something like n factorial is huge. How could it ever be reasonable? Well, because you're taking a log of something huge. When you take a log of something huge, what does it make? It makes it into not small, right? Something huge is still only going to become reasonable, right? Okay. All right. So let's set up our inequality. Log of n factorial. Once again, we want to make this look like c n log n. Right? There we go. There. I don't need that one right there. N log n. Okay. So what? If I were to write this out, and again, this is called factorial. Another name for this is the gamma function. Right? So how can I express this? This is n times n minus 1 times n minus 2 times ... 3 times 2 times 1. If you just look at these terms right here, what is the highest order term? What is the largest term? N. Right? For all n greater than or equal to 1, right? Because we don't deal with zeros here. So what could I do? What if I replaced every single one of these with n? Right? Replace the second one with n. Replace the third one with n, ... n, 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 for all n greater than or equal to 1. Right? Okay? Because we don't want to deal with zeros either because we've got logs here, right? And log of 0 is undefined. That's equal to log of, if I have n times n times n, n times, how many n's is that? N to the n. Right? Now, once again, pull out your log identities from way back when. What can you do with exponents within a log? Pull it out front. Hey, guess what that looks like now? For c being 1 and n not being 1, because we don't want to deal with zeros with logs, the inequality holds here. By the way, the inequality holds the other direction too. Right? You just have to... Yeah, the other direction, I think you're going to have to bring in Stirling's formula. Right? But otherwise, there you go. Right? So, several examples illustrating that you've got to be a little bit clever about your inequalities. Some things are pretty straightforward, especially if it's just a polynomial or something like that. And if you need practice with polynomials, go ahead and go for it. But otherwise, those are your examples. All right? So, let's go ahead and start talking about what do you do when you've got a recursive algorithm instead. Right? How do you analyze a recursive algorithm? Right? So first of all, let's go ahead and review merge sort. Merge sort. So that we actually have an algorithm to contemplate how to go about doing this. Did we do merge sort in CS1? I think maybe, maybe not. But anyway, in any case, let's do it now. Right? Here's the basic idea. All right. First of all, you split it in half. In fact, let me visualize it over here. Right? So let's just go ahead and give me some random numbers here. 2, 8, 7, 40, 3, 2, 1, 5. Right, there we go. I've got 8 numbers. Now what I'm going to do is I'm going to do a divide and conquer strategy. I'm going to divide this into a left partition and a right partition. And then I'm going to recursively sort each one of those. Well, if I can split up 8 into 4 and 4, I can certainly split up 4 into 2 and 2. So this gets split out again into 2 and 8, and 7 and 40, 3, 2, and 1, 5, comma, comma, comma. Now, if I could split 8 into 4 and 4, and 4 into 2 and 2, I can split them into 1s as well. 7, 40, 3, 2, and then 1 and 5. Now, just looking at an array or a collection of one element, do you have to do anything to make it sorted? Nope. So, by definition, every single one of these 8 lists that I've split it up into are now sorted. Now, we go into a merge phase, where if I'm given 2 sorted arrays, how can I zipper them together so that they're all merged? So I'm going to go ahead and fast forward this. 2, 7, 8, 40, and then 1, 2, 3, and 5. Right? How would we go about merging these together? Let me go ahead and bring this to the next. I think it's that one. Nope. Ah, darn it. All right, undo. Copy. And paste. There we go. All right. I'm going to keep two I and j here. Two variables, I and j. And then I'm going to copy it to a resulting array that has k here instead. This is A, or left, and this is B, right, and then this is C. I'm going to merge these two into one sorted array. Now, because this is already sorted and because this is already sorted, I can use that to my advantage here. Let me go ahead and, can I select everything and move it down? There we go. I lost my I, but whatever. All right. Okay. Now, I'm going to look at the left and I'm going to look at the right. Which one of these is smaller? The one from the right. So I end up copying that down over here. 1. I also, at the same time, advance my pointer here, or my reference, to the next one. I also advance my k to the next one. I am now looking at 2 and 2. Break ties arbitrarily, but let's just go ahead and break ties preferring A over here. So I copy over 2. Right? And I move forward my I over here. Right? Now I'm looking at 2 and 7, so I end up copying 2 over next. And advancing my j. You can fast forward here. 3 gets copied. 3 gets copied. 5 gets copied. Right? At that point, j is no longer pointing to anything valid. Do we need to make any more comparisons? Just zipper everything over. All of this stuff gets copied over. 7, 8, and 40. There we go. I've merged those two together. The first initial step was the divide. The second step, the merge step, was conquering it. Right? Merging it together, zippering it together. Right? Until you came back from this. Right? So, the goal is to break it into 2 equal parts first, until you have a subarray that is less than or equal to 1. Of course, I chose 8 there because it was nice that it would divide like that. But if there were like 7, right? How would you end up dividing that? Well, it would be 4 and 3, and then 3 would be 2 and 1, and then 1 would be divided into 0 and 1. But you know, you're already there, right? So you just need a stopping point, basically. As you return from the recursion, you merge the 2 sorted arrays together just like I showed, all right? So let's take a look at the pseudocode first. Pseudocode. Hopefully I have it. I should have checked that. Merge, sort. There we go. There it is. Okay. There's the main merge sort algorithm, right? Left and right, those are your index values. Oh, sorry. There we go. There we go. Left and right are your index values, right? You split it by simply taking the average. That technique looks like we've seen it before, right? Binary search, got left and right, you need to find the middle value. Then you call this subroutine called merge sort, this merge sort, on the array, the left, and then m. Right? And then the right partition is m plus 1 all the way up to r. Right? Here it's not m minus 1 because, well, what about that one element in the middle, right? It's not yet sorted. It needs to go either left or right. We prefer it to go left. Right? Now, once L and R have passed each other, or once they're equal, right? If it's equal, then we never actually do this, and we output A, or return A, right? But if they've gone past each other, then if they're equal, then that means that the size of the array is 1. If they've gone past each other, then that means that the size of the array is 0 because it's empty. Okay, that's half of it. Oops. Do I have the merge? Actually, no. Let's do it on the next page. There it is. Merge. That's a little bit more complicated. But it's the same basic idea as I showed you. We establish an I and a J. I is going to start at L, the left partition. J is going to start at 1 on the right partition. K is going to start on as the index value that you're copying to in the merged A right here. Right? While I is less than n and j is less than m, we do the following. Right? If the left partition has a smaller value than the right partition, then we copy over the left partition and advance my I. Otherwise, we copy over the right partition's element, and we advance j. In either case, we advance k. We get out of this while loop because at least one collection is empty. So we blindly copy either A, or the left partition, or the right partition here. Now, if the left partition is empty, then this while loop will never actually execute because I has already exceeded n. Likewise for j on the m partition. Here, the left is of size n and the right is of size m. Right? So this is the merge, and then at some point you break out because you just blindly copy over the rest of it. Okay? That's merge sort. We're going to come back to this pseudocode here in a second. Right? So what about the analysis? Right? So to analyze recursive algorithms, first of all, you need to define a recursion. Right? So you define a recursive function that captures the idea of work of the elementary operation. Right? You set up a recursion. Work the elementary. In other words, how many calls? Here, I'll do it like this. How many calls to the function do you make, and how big is the input size for each call? Right? Those are the things that you need to answer. Then you solve the recursion. I'm not going to number the, 1, 2, I'll just bullet point them. There we go. Bullet points are better. Right? You solve the recursion. Or, better yet, use a tool. Right? ... I'll talk about what that tool here is in a second. For now, let's go ahead and come over here to this pseudocode here. And let's set up a notion of work. First of all, what is the elementary operation here? Right? So what are we basically doing? Well, we're doing an addition, we're doing a division, we're doing a floor, we're doing assignments here. But really, this subroutine and this subroutine, that's where all the magic happens. So let's pay attention to that. Right? Now, what do you think the worst case scenario might be here? Let me show you what the worst case scenario would be. What if it's all interleaved? 5 and 7. There's one of them. And then the other one is 2, 4, 6, and 8. How many comparisons am I going to make in order to merge this all together? Right? Well, I'm going to compare 2 to 1, seeing that I need to copy over 1. Right? Now I'm paying attention to 3 and 2. Now I copy over 2. Keep a running total here, by the way, on my finger. Right? This gets moved over to this one. Right? Now I copy over 3, right? And that gets moved over. There we go. I'm going to copy over 4, 5, 6, 7, and I've run out of fingers, by the way. 7, 8, right? So how many did you actually compare? The first 7. Not the last one. Why? Because the last one gets copied blindly. Right? Why is this the worst case scenario? Well, what's the best case scenario? 1, 2, 3, 4, 5, 6, 7, 8, right? You end up making a comparison of 1 to 5, 2 to 5, 3 to 5, 4 to 5, right? You end up making n divided by 2 comparisons and end up copying everything else over blindly, right? Otherwise, you're going to do something in between there, right? So in the best case, you only end up doing, say, n divided by 2 comparisons. In the worst case, how many were there? N minus 1, right? This is the worst. Right? Are those two appreciably different? That's the difference between the worst case running time of linear search and the average case running time of linear search. They're still going to both be linear. So let's go ahead and pay attention to that one right there. Right? So in the worst case, let's come back up here, analysis. In the worst case, the merge subroutine requires n minus 1 comparisons. Right? And by the way, our elementary operation is the comparison in the merge subroutine. Okay. Elementary. Right, there we go. All right. So, how many times is the merge subroutine called and on what input sizes? All right. For that, I'm going to set up a recursion. Okay. I'm going to say that C sub n is equal to the number of comparisons by merge sort. And by merge sort, I mean that main routine, not this subroutine, but this main routine over here. All right, this merge sort routine right here. Okay? And I'm just going to say that C sub n is equal to the number of comparisons made by merge sort on input of size n. Okay? We need to get a handle on what C sub n looks like. Okay? So let's go back to the pseudocode for the main for the main routine here, right? Okay. Well, all right, merge sort on something of size n, right? That gives me C sub n. That's what I have to solve here, right? Either it's nothing, in which case we're done, right? That happens at the end. Otherwise, the more common case is that we're going to have to split this into two. We make one call on merge sort, one recursive call on merge sort on an array about how big. If we received an array of size n, then how big is it going to be when we call this subroutine over here? N divided by 2. Likewise, this one, the right one, is going to be n divided by 2. Right? So, C sub n is equal to C of n divided by 2 plus C sub n divided by 2. This is going to be the recursive call on the left partition. This is going to be the recursive call on the right partition. Right? Be careful. You're still doing some other work here. Right? When you come back from these recursive calls, you make a call to this subroutine right here to merge them together. And we just said that to do that in the worst case, how many comparisons does it make? N minus 2. Or sorry, n minus 1. N minus 1. And this is going to be the non-recursive merge work. Right? All right. So all together, what do we have here? I'm going to simplify this. 2 calls to two recursive calls on an input 1/2 as large with a non-recursive cost of n minus 1. We've got enough time, we could solve this. Do you know how to solve this? All right, you just unfold it. So I need to get rid of this term. If I plug n minus 2, n divided by 2 over here, what do I get? C2 times C sub n divided by 2 gives me 4, right? There we go. Oh, and then, careful, this is tricky, plus n divided by 2 minus 1, right? That's all right there. I'm just taking this and expanding it out. Don't forget everything else, n minus 1, right? Do that again. I need to get rid of C sub n divided by 4. Plug the n divided by 4 over here, and you get n divided by 4 divided by 2, so that ends up being n divided by 8, plus n divided by 4 over here. So what does that end up being? 2 times C sub... Now I've already lost it. I lost my 2, right? There we go. 2 C n divided by 8 C, there we go, plus n divided by 8 minus 1, sorry, 4. And then don't lose everything else. So this is, actually this 2 will cancel with this 2, so what do you have? N minus 2 plus n minus 1. There we go. keep those in parentheses because you're going to want to you're going to want a pattern to emerge, basically. Yeah, we did. Damn it. All right. Anyway, I don't want to solve it. Right. You see how complex this can be anyway, right? Instead, what I'm going to do is I'm going to bring in a tool. That tool is, have you seen it before? The master theorem. Right, there we go. I'm going to put master in double quotes there because it's not really the master of anything, right? It's only if you have a recurrence of this form, right? Where you are making a recursive calls on an input that has been cut by a factor of b, and then you're making some non-recursive work. Right? You're doing some non-recursive work here. Right? And then you've got all these caveats that have to apply, and also that it has to be smooth and everything, whatever. Stuff goes beyond this course. Right? If you have something that looks like this, then you can plug and chug. Right? If a is strictly less than b to the d, then that means that you are doing fewer recursive calls than you are doing recursive work. Oh, by the way, what is d here? Sorry. F of n here is bounded by some polynomial n to the d. All right? So this is that you're doing less recursion and more non-recursive work. This means that you are doing more recursion and less non-recursive work. This means that you are evening things out. And this is always where we end up being anyway. The master theorem has several applications, but for all the applications we're going to see, it's going to be case 2. Why? Well, come over here and let's go ahead and cross all this out. Yeah, right. All that red there, right? Now I regret that because I crossed out the one thing I wanted to leave. Right, there we go. Where I've got 2c sub n divided by 2 plus n minus 1. All we have to do is identify a, b, and then d. And then we plug and chug. Right? So in this case, what is a? 2. B is 2. And d ends up being what? We've got this being n minus 1 is big O of n to the first. Good. So a versus b to the d. In this case, it's 2 versus 2 to the first. They are equal. And so by case 2 of the master theorem, we have that c sub n is order n to the d, but d was 1, you told me, right? 1 log n. Right? Merge sort is an optimal algorithm with respect to sorting there. Right? Okay. And all you need to do is use the master theorem here. When we do, we can try that again if we wanted to try it with quicksort analysis instead. But when you're solving have you done recurrences? It's like second order linear homogeneous recurrence relations in 235? No? Okay. Arbitrary order non-homogeneous recurrence relations? No. Okay. Have you taken Math 221, ordinary differential equations? Then you've done all the work. You just did it on a continuous domain instead of a discrete domain, right? And so what you end up doing is you end up setting up these polynomials, right, and finding the roots. And once you've found the roots, then you plug and chug. And with ordinary differential equations, it's also if it's of this form, then look for a solution of this form. And they've got this big giant table of solutions, right? If it's got a sine, then you do this. And if it's got a cosine, you do that, and whatever, right? And then you ask your analysis teacher, like I did 20 years ago, like, what's the intuition behind that? Why do you have this big table, lookup table? And you go, well, people tried 50 things, and the 51st thing worked, and that's what went into the table, right? There's no intuition to it that he could give me, right? But in any case, we're not going to solve them because everything that we're going to be dealing with is simple master theorem here, okay? Almost all of your algorithms, recursive algorithms that you'll be dealing with are like that, right? But again, what you do is you have to set up a recursion, right? And the questions that you have to ask yourself are how many recursive calls do you make and how big is the input size for each call? And what is the non-recursive cost? That's what I should have added. What is the non-recursive cost, right? That's why we look at non-homogeneous recurrence relations, because there's a non-recursive cost there. They're not homogeneous, right? Let's do another one really quick. Binary search. Right? So, I only ever present the iterative version of binary search, but indeed there is a recursive version of binary search. Right? There it is. Right? So we're taking a sorted collection and then bounds L and R and a key. And if L has exceeded R, then we're done. We output no. Otherwise, we compute that middle index. And if that's the thing that we're looking for, we're done. Otherwise, if that the thing that we're looking for is greater than the middle element, then we need to search in the right. So we recurse on m plus 1 to R. Otherwise, we recurse left, L, and then m minus 1. Once again, what is our elementary operation here? Well, the same as before our other analysis, that we're going to collapse that down into one comparison. Right? So our non-recursive cost here is one comparison. This is the non-recursive comparison on lines 5/7. Right? All right, so setting up our recursion here, how many recursive calls do you actually make? Remember, this is if, else. So do I actually make both of those recursive calls? Nope. I make one recursive call on an input half as big. Right? And that's it. So C sub n is equal to C of n divided by 2 plus 1. What is my A? 1. What is my B? 2. What is my D? Right? Yeah, 0. Good. Right? That always trips people up, right? 1 is equal to order n to the 0, because that's equal to order 1. Right? All right, so A versus B to the D. In other words, 1 versus 2 to the 0. They're equal. Guess what? Case 2 again. Right? That's all that ever comes up. It's really, really boring until you get to, like, I don't know, what matrix multiplication algorithms. So it's n to the d log n. Right? Well, what was d here? 0. So n to the 0 is 1, and we've got that this is equal to order log n. Same exact analysis as if we had done it the proper way of using iterations instead of recurrence. Right? All right, so if you're ever in need of of analyzing this stuff with respect to recursion, right, then you have to follow this outline here, where you set up a recurrence, and then either you have to solve it, in which case good luck, ordinary differential equation world, or you just use master theorem to provide an asymptotic analysis of it. All right, so we'll pick it up there maybe with Wednesday.